In this video, I'd like to start to talk about clustering. This will be exciting because this is our first unsupervised learning algorithm where we learn from unlabeled data instead of from labeled data. So what is unsupervised learning? I briefly talked about unsupervised learning at the beginning of the class, but it's useful to contrast it with supervised learning. So here's a typical supervised learning problem where we're given a labeled training set and the goal is to find the decision boundary that separates the positive labeled examples and the negative labeled examples. So the supervised learning problem in this case is given a set of labels to fit a hypothesis to it. In contrast, in the unsupervised learning problem, we're given data that does not have any labels associated with it. So we're given data that looks like this. Here's a set of points and then no labels. And so our training set is written just x1, x2, and so on up to xm, and we don't get any labels y, and that's why the points plotted up on the figure don't have any labels with them. So in unsupervised learning, what we do is we give this sort of unlabeled training set to an algorithm, and we just ask the algorithm, find some structure in the data for us. Given this data set, one type of structure we might have an algorithm find is that it looks like this data set has points grouped into two separate clusters, and so an algorithm that finds clusters like the ones I've just circled is called a clustering algorithm, and this will be our first type of unsupervised learning, although there will be other types of unsupervised learning algorithms that we'll talk about later that finds other types of structure or other types of patterns in the data other than clusters. We'll talk about this after we've talked about clustering. So what is clustering good for? Early in this class, I'd already mentioned a few applications. One is market segmentation, where you may have a database of customers and want to group them into different market segments so you can sell to them separately or serve your different market segments better. Social network analysis. There are actually groups that have done this. Things like looking at a group of people's social networks, so things like Facebook, Google+, or maybe information about who are the people that you email the most frequently and who are the people that they email the most frequently, and to find coherent groups of people. So this would be another maybe clustering algorithm where you want to find who are the coherent groups of friends in a social network. Here's something that one of my friends actually worked on, which is use clustering to organize compute clusters or to organize data centers better, because if you know which computers in the data center and the cluster tend to work together, you can use that to reorganize your resources and how you lay out the networks and how you design your data center and communications. And lastly, something that actually another friend worked on, using clustering algorithms to understand galaxy formation and using that to understand how to understand astronomical data. So that's clustering, which is our first example of an unsupervised learning algorithm. In the next video, we'll start to talk about a specific clustering algorithm. In the clustering problem, we are given an unlabeled data set, and we would like to have an algorithm automatically group the data into coherent subsets or into coherent clusters for us. The k-means algorithm is by far the most popular and by far the most widely used clustering algorithm. And in this video, I'd like to tell you what the k-means algorithm is and how it works. The k-means clustering algorithm is best illustrated in pictures. Let's say I want to take an unlabeled data set like the one shown here, and I want to group the data into two clusters. If I run the k-means clustering algorithm, here's what I'm going to do. The first step is to randomly initialize 2 points called the cluster centroids. So these two crosses here, these are called the cluster centroids, and I have 2 of them because I want to group my data into 2 clusters. K-means is an iterative algorithm, and it does 2 things. First is a cluster assignment step, and second is a move centroid step. So let me tell you what those things mean. The first of the 2 steps in the inner loop of k-means is this cluster assignment step. What that means is that it's going to go through each of the examples, each of these green dots shown here, and depending on whether it's closer to the red cluster centroid or the blue cluster centroid, it's going to assign each of the data points to one of the 2 cluster centroids. Specifically, what I mean by that is going to go through your data set and color each of the points either red or blue, depending on whether it's closer to the red cluster centroid or the blue cluster centroid. And I've done that in this diagram here. So that was the cluster assignment step. The other part of k-means, the inner loop of k-means, is the move centroid step. And what we're going to do is we're going to take the two cluster centroids, that is the red cross and the blue cross, and we're going to move them to the average of the points colored the same color. So what I'm going to do is look at all the red points and compute the average, that's really the mean of the location of all the red points, and we're going to move the red cluster centroid there. And the same thing for the blue cluster centroid. Look at all the blue dots and compute their mean, and then move the blue cluster centroid there. So let me do that now. We'll move the cluster centroids as follows. And I've now moved them to their new means. Right? So the red one moved like that, and the blue one moved like that, and the red one moved like that. And then we go back to another cluster assignment step. So we're again going to look at all of my unlabeled examples, and depending on whether it's closer to the red or the blue cluster centroid, I'm going to color them either red or blue. So I'm going to assign each point to one of the two cluster centroids. So let me do that now. And so the colors of some of the points just changed. And then I'm going to do another move centroid step. So I'm going to compute the average of all the blue points, compute the average of all the red points, and move my cluster centroids like this. And so let's do that again. Let me do one more cluster assignment step. So color each point red or blue based on what it's closer to, and then do another move centroid step. And we're done. And in fact, if you keep running additional iterations of k-means from here, the k-means, the cluster centroids will not change any further, and the colors of the points will not change any further. And so, this is the at this point, k-means has converged, and it's done a pretty good job finding the two clusters in this data. Let's write out the k-means algorithm more formally. The k-means algorithm takes two inputs. One is a parameter k, which is the number of clusters you want to find in the data. I'll later say how we might go about trying to choose k, but for now, let's just say that we've decided we want a certain number of clusters, and we're going to tell the algorithm how many clusters we think there are in the data set. And then k-means also takes as input this sort of unlabeled training set of just the x's, and because this is unsupervised learning, we don't have the labels y anymore. And for unsupervised learning, or for k-means, I'm going to use the convention that xi is an Rn dimensional vector. And that's why my training examples are now n dimensional rather than n+1 dimensional vectors. This is what the k-means algorithm does. The first step is that it randomly initializes k cluster centroids, which we want to call mu1, mu2, up to mu k. And so in the early diagram, the cluster centroids corresponded to the location of the red cross and the location of the blue cross. So there we had two cluster centroids, so maybe the red cross was mu1 and the blue cross was mu2, and more generally we would have k cluster centroids rather than just two. Then the inner loop of k-means does the following. We're going to repeatedly do the following. First, for each of my training examples, I'm going to set this variable ci to be the index 1 through k of the cluster centroid closest to xi. So this was my cluster assignment step, where we took each of my examples and colored it either red or blue, depending on which cluster centroid it was closest to. Okay? So ci is going to be a number from 1 to k that tells us, is it closer to the red cross or is it closer to the blue cross? And another way of writing this is I'm going to, to compute ci, I'm going to take my ith example xi, and I'm going to measure its distance to each of my cluster centroids. This is mu and then a lowercase k, right? So capital K is the total number of centroids, and I'm going to use lowercase k here to index into the different centroids. But so ci is I'm going to sort of minimize over my values of k and find the value of k that minimizes this distance between xi and the cluster centroid, and then the value that minimizes the value of k that minimizes this, that's what gets set in ci. So here's another way of writing out what ci is. If I write the norm between xi minus mu k, then this is the distance between my ith training example xi and the cluster centroid mu subscript k. This here, that's a lowercase k. So uppercase K is going to be used to denote the total number of cluster centroids, and this lowercase k, lowercase k is a number between 1 and capital K. I'm just using lowercase k to index into my different cluster centroids. That's this lowercase k. So that's the distance between the example and the cluster centroid, and so what I'm going to do is find the value of k, of lowercase k, that minimizes this, and so the value of k that minimizes this, that's what I'm going to set as CI. And by convention, here I've written the distance between xi and the cluster centroid. By convention, people actually tend to write this as the squared distance. So we think of CI as picking the cluster centroid with the smallest squared distance to my training example xi. But of course, minimizing squared distance and minimizing the distance, that should give you the same value of CI. But we usually put in the square there just as a convention that people use for k-means. So that was the cluster assignment step. The other inner loop of k-means does the move centroid step. And what that does is, for each of my cluster centroids, so for lowercase k equals 1 through k, it sets mu k equals to the average of the points assigned to cluster. So as a concrete example, let's say that one of my cluster centroids, let's say cluster centroid 2, has training examples 1, 5, 6, and 10 assigned to it. And what this means is this means that C1 equals to C5 equals to C6 equals to, and similarly, well, C10 equals to, right? If we got that from the cluster assignment step, then that means that examples 1, 5, 6, and 10 were assigned to cluster centroid 2. Then in this move centroid step, what I'm going to do is just compute the average of these four things. So I'm going to x1 plus x5 plus x6 plus x10, and then I'm going to average them. So here I have 4 points assigned to this cluster centroid, so just take 1/4 of that, and now mu2 is going to be an n-dimensional vector, because each of these examples, x1, x5, x6, x10, each of them were an n-dimensional vector. And when I add up these things and divide by 4, because I have 4 points assigned to this cluster centroid, I end up with my move centroid step for my cluster centroid mu2, and this has the effect of moving mu2 to be the average of those 4 points listed here. One thing that I've sometimes been asked is, well, here we said let's let mu k be the average of the points assigned to that cluster, but what if there's a cluster, what if there's a cluster centroid with no points, with 0 points assigned to it? In that case, the more common thing to do is to just eliminate that cluster centroid, and if you do that, you end up with k-1 clusters instead of k clusters. But sometimes if you really need k clusters, then the other thing you can do if you have a cluster centroid with no points assigned to it is you can just randomly reinitialize that cluster centroid. But it's more common to just eliminate a cluster if somewhere during k-means it ends up with no points assigned to that cluster centroid. And that can happen, although in practice it happens not that often. So that's the k-means algorithm. Before wrapping up this video, I just want to tell you about one other common application of k-means, and that's to the problems with non-well separated clusters. Here's what I mean. So far we've been picturing k-means and applying it to data sets like that shown here, where we have 3 pretty well separated clusters, and we'd like an algorithm to find maybe the 3 clusters for us. But it turns out that very often k-means is also applied to data sets that look like this, where they may not be several very well separated clusters. Here's an example application to t-shirt sizing. So let's say you're a t-shirt manufacturer, and what you've done is you've gone to the population that you want to sell t-shirts to, and you've collected a number of examples of the height and weight of these people in your population. So and I guess height and weight tend to be positively correlated, and so maybe you end up with a data set like this, with a sample, with a set of examples of different people's heights and weight. Let's say you want to size your t-shirts. Let's say I want to design and sell t-shirts of 3 sizes: small, medium, and large. So how big should I make my small, and how big should I make my medium, and how big should I make my large t-shirts? One way to do this would be to run the k-means clustering algorithm on this data set that I have shown on the right. And maybe what k-means will do is group all of these points into one cluster, and group all of these points into a second cluster, and group all of those points into a third cluster. So even though the data, beforehand it didn't seem like we have three well-separated clusters, k-means will kind of separate separate out the data into multiple clusters for you. And what you can do is then look at this first population of people and look at them and look at the height and weight and try to design a small t-shirt so that it kind of fits this first population of people well, and then design a medium t-shirt and design a large t-shirt. And this is in fact kind of an example of market segmentation, where you're using k-means to separate your market into three different segments, so you can design a product separately, that is the small, medium and large t-shirts, that tries to suit the needs of each of your three separate subpopulations well. So that's the k-means algorithm, and by now you should know how to implement the k-means algorithm and kind of get it to work for some problems. But in the next few videos, what I want to do is really get more deeply into the nuts and bolts of k-means and talk a bit about how to actually get this to work really well. Most of the supervised learning algorithms we've seen, things like linear regression, logistic regression, and so on, all of those algorithms had an optimization objective or some cost function that the algorithm was trying to minimize. It turns out that k-means also has an optimization objective or a cost function that is trying to minimize. And in this video, I'd like to tell you what that optimization objective is. And the reason I want to do so is because this will be useful to us for two purposes. First, knowing what is the optimization objective of k-means will help us to debug the learning algorithm and just make sure that k-means is running correctly. And second, and perhaps even more importantly, in a later video, we'll talk about how we can use this to help k-means find better clusters and avoid local optima. But we'll do that in a later video that follows this one. Just as a quick reminder, while k-means is running, we're going to be keeping track of two sets of variables. First is these CIs, and that keeps track of the index or the number of the cluster to which an example xi is currently assigned. And then the other set of variables we use is mu subscript k, which is the location of cluster centroid k. And again, for k-means we use capital K to denote the total number of clusters, and here lowercase k is going to be an index into the cluster centroids, and so lowercase k is going to be a number between 1 and capital K. Now here's one more bit of notation, which is going to use mu subscript ci to denote the cluster centroid of the cluster to which example xi has been assigned, right? And here's to explain that notation a little bit more. Let's say that xi has been assigned to cluster number 5. What that means is that ci, that is the index of xi, that is equal to 5, right? Because having ci equals 5, that's what it means for the example xi to be assigned to cluster number 5. And so mu subscript ci is going to be equal to mu subscript 5, because ci is equal to 5. And so this mu subscript ci is the cluster centroid of cluster number 5, which is the cluster to which my example xi has been assigned. Armed with this notation, we're now ready to write out what is the optimization objective of the k-means clustering algorithm. And here it is. The cost function that k-means is minimizing is a function j of all of these parameters, c1 through cm and mu1 through mu k, that k-means is varying as the algorithm runs. And the optimization objective is shown on the right is the average, or 1 over m, of sum from I equals 1 through m of this term here that I've just drawn the red box around, right, of the squared distance between each example xi and the location of the cluster centroid to which xi has been assigned. So let me just draw this in, let me just explain this, right? So here's the location of training example xi, and here's the location of the cluster centroid to which example xi has been assigned. So to explain this in pictures, if here's x1, x2, and if a point here is my example xi, so if that is equal to my example xi, and if xi has been assigned to some cluster centroid, I'm going to denote my cluster centroid with a cross. So if that's the location of mu 5, let's say, if xi has been assigned to cluster centroid 5, as in my example up there, then this squared distance, that's the squared of the distance between the point xi and this cluster centroid to which xi has been assigned. And what k-means can be shown to be doing is that it is trying to find parameters ci and mu I, trying to find c and mu to try to minimize this cost function j. This cost function is sometimes also called the distortion cost function, or the distortion of the k-means algorithm. And just to provide a little bit more detail, here's the k-means algorithm. Here's exactly the algorithm as we have written it out on the earlier slide. And what this first step of this algorithm is, this was the cluster assignment step, where we assign each point to the cluster centroid. And it's possible to show mathematically that what the cluster assignment step is doing is exactly minimizing j, with respect to the variables c1, c2, and so on up to cm, while holding the cluster centroids mu1 up to mu k fixed. So what the cluster assignment step does is, it doesn't change the cluster centroids, but what it's doing is exactly picking the values of c1, c2 up to cm that minimizes the cost function or the distortion function j. And it's possible to prove that mathematically, but I won't do so here. But it has a pretty intuitive meaning of just, well, let's assign each point to the cluster centroid that is closest to it, because that's what minimizes the squared distance between the point and its corresponding cluster centroid. And then the other part of the second step of k-means, this second step over here, the second step was the move centroid step. And once again, I won't prove it, but it can be shown mathematically that what the move centroid step does is it chooses the values of mu that minimizes j. So it minimizes the cost function j with respect to, WRT is my abbreviation for with respect to, but it minimizes j with respect to the locations of the cluster centroids mu1 through mu capital K. So what k-means really is doing is just taking the two sets of variables and partitioning them into two halves, right? You have first the c sets of variables, and then you have the mu sets of variables. And what it does is it first minimizes j with respect to the variable c, and then minimizes j with respect to the variables mu, and then it keeps on iterating. And so that's all that k-means does. And now that we understand k-means as trying to minimize this cost function j, we can also use this to try to debug our learning algorithm and just kind of make sure that our implementation of k-means is running correctly. So we now understand the k-means algorithm as trying to optimize this cost function j, which is also called the distortion function. We can use that to debug k-means and help make sure that k-means is converging and is running properly. And in the next video, we'll also see how we can use this to help k-means find better clusters and help k-means to avoid local optima. In this video, I'd like to talk about how to initialize k-means. And more importantly, this will lead into a discussion of how to make k-means avoid local optima as well. Here's the k-means clustering algorithm that we talked about earlier. One step that we never really talked much about was this step of how you randomly initialize the cluster centroids. There are a few different ways that one could imagine using to randomly initialize the cluster centroids, but it turns out that there's one method that's much more recommended than most of the other options one might think about. So let me tell you about that option, since it's what often seems to work best. Here's how I usually initialize my cluster centroids. When running k-means, you should have the number of cluster centroids k set to be less than the number of training examples m. It would be really weird to run k-means with a number of cluster centroids that's equal or greater than the number of examples you have, right? So the way I usually initialize k-means is I would randomly pick k training examples. So, and what I do is then set mu1 up to mu k equal to these k examples. Let me show you a concrete example. Let's say that k is equal to 2, and so on this example on the right, let's say I want to find 2 clusters. So what I'm going to do in order to initialize my cluster centroids is I'm going to randomly pick a couple examples. And let's say I pick this one and I pick that one. And the way I'm going to initialize my cluster centroids is I'm just going to initialize my cluster centroids to be right on top of those examples. So that's my first cluster centroid, and that's my second cluster centroid, and that's one sort of random initialization of k-means. The one I drew looks like a particularly good one. Sometimes I might get less lucky, and maybe I'll end up picking that as my first randomly chosen example, and that as my second one. And here I'm picking two examples because k equals 2. So I'm going to randomly pick two training examples. And if I chose those two, then I'll end up with maybe this as my first cluster centroid, and that as my second initial location of the cluster centroid. So that's how you can randomly initialize the cluster centroids. And so at initialization, your first cluster centroid, mu1, will be equal to xi for some randomly value of I, and mu2 will be equal to xj for some different randomly chosen value of j, and so on if you have more clusters and more cluster centroids. As sort of a side comment, I should say that in the earlier video where I first illustrated k-means with an animation, in that set of slides, only for the purpose of illustration, I actually used a different method of initialization for my cluster centroids. But the method described on this slide, this is really the recommended way, and the way that you should probably use when you implement k-means. So as is suggested perhaps by these two illustrations on the right, you might be able to guess that k-means can end up converging to different solutions depending on exactly how the clusters were initialized. And so depending on the random initialization, k-means can end up at different solutions. And in particular, k-means can actually end up at local optima. If you're given a data set like this, well, it looks like, there are 3 clusters. And so if you run k-means, and if it ends up at a good local optima, this might be really the global optimum, you might end up with that clustering. But if you had a particularly unlucky random initialization, k-means can also get stuck at different local optima. So in this example on the left, it looks like the blue cluster has captured a lot of points on the left, and then the red and the green clusters each is capturing only a relatively small number of points. And so this corresponds to a bad local optima because it has basically taken these two clusters and merged them into one, and furthermore it has split the second cluster into two separate subclusters like so. And it has also taken the second cluster and split it into 2 separate subclusters like so. And so both of these examples on the lower right correspond to different local optima of k-means. And in fact, in this example here, the red cluster has captured only a single unlabeled example. And the term local optima, by the way, refers to local optima of this distortion function j. And what these solutions on the lower left, what these local optima correspond to is really solutions where k-means has gotten stuck at the local optima and is not doing a very good job minimizing this distortion function j. So if you're worried about k-means getting stuck in local optima, if you want to increase the odds of k-means finding the best possible clustering like that shown on top here, what we can do is try multiple random initialization. So instead of just initializing k-means once and hoping that that works, what we can do is initialize k-means lots of times and run k-means lots of times, and use that to try to make sure we get as good a solution, as good a local or global optimum as possible. Concretely, here's how you could go about doing that. Let's say I decide to run k-means 100 times. So I'm going to execute this loop 100 times. And a fairly typical number of times to run k-means would be something from 50 up to maybe 1,000. So, but let's say you decide to run k-means 100 times. So what that means is we would randomly initialize k-means, and for each of these sort of 100 random initializations, we would run k-means, and that would give us a set of clusterings and a set of cluster centroids. And we would then compute the distortion j, that is compute this cost function, on the set of cluster assignments and cluster centroids that we got. Finally, having done this whole procedure 100 times, you will have 100 different ways of clustering the data. And then finally, what you do is, out of these 100 ways we've found of clustering the data, just pick one that gives us the lowest cost, that gives us the lowest distortion. And It turns out that if you're running k-means with a fairly small number of clusters, so if the number of clusters is anywhere from 2 up to maybe 10, then doing multiple random initializations can sometimes make sure that you find a better local optimum, make sure that you find a better clustering of the data. But if k is very large, so if k is much greater than 10, certainly if k were, if you're trying to find hundreds of clusters, then having multiple random initializations is less likely to make a huge difference, and there's a much higher chance that your first random initialization will give you a pretty decent solution already. And doing multiple random initializations will probably give you a slightly better solution, but maybe not that much. But it's really in the regime of when you have a relatively small number of clusters, especially if you have maybe 2 or 3 or 4 clusters, that random initialization could make a huge difference in terms of making sure you do a good job minimizing the distortion function and giving you a good clustering. So that's k-means with random initialization. If you're trying to learn a clustering with a relatively small number of clusters, 2, 3, 4, 5, maybe 6, 7, using multiple random initializations can sometimes help you find much better clusterings of the data. But even if you're learning a large number of clusters, the initialization, the random initialization method that I described here, that should give k-means a reasonable starting point to start from for finding a good set of clusters. In this video, I'd like to talk about one last detail of k-means clustering, which is how to choose the number of clusters, or how to choose the value of the parameter capital K. To be honest, there actually isn't a great way of answering this or of doing this automatically, and by far the most common way of choosing the number of clusters is still choosing it manually by looking at visualizations or by looking at the output of the clustering algorithm or something else. But I do get asked this question quite a lot of how do you choose the number of clusters, and so just want to tell you, what are people's current thinking on it, although the most common thing is actually to choose the number of clusters by hand. A large part of why it might not always be easy to choose the number of clusters is that it's often genuinely ambiguous how many clusters there are in the data. Looking at this data set, some of you may see 4 clusters, and that would suggest using k equals 4, or some of you may see 2 clusters, and that will suggest k equals 2, and yet others may see 3 clusters. And so looking at the data set like this, the true number of clusters, it actually seems genuinely ambiguous to me, and I don't think there is one right answer. And this is part of unsupervised learning. We aren't given labels, and so there isn't always a clear-cut answer. And this is one of the things that makes it more difficult to, say, have an automatic algorithm for choosing how many clusters to have. When people talk about ways of choosing the number of clusters, one method that people sometimes talk about is something called the elbow method. Let me just tell you a little bit about that and then mention some of its advantages but also shortcomings. So in the elbow method, what we're going to do is vary k, which is the total number of clusters. So we're going to run k-means with one cluster. That means really everything gets grouped into a single cluster, and compute the cost function, or compute the distortion j, and plot that here. And then we're going to run k-means with 2 clusters, maybe with multiple random initializations, maybe not. But then, with 2 clusters, we should get hopefully a smaller distortion, so plot that there. And then run k-means with 3 clusters. Hopefully you get even smaller for the distortion, and plot that there. And run k-means with 4, 5, and so on. And so we end up with a curve showing how the distortion goes down as we increase the number of clusters. And so we get a curve that maybe looks like this. And if you look at this curve, what the elbow method does is it says, well, let's look at this plot. Looks like there's a clear elbow there, right? This is maybe by analogy to the human arm, where if you imagine that you reach out your arm, then this is your shoulder joint, this is your elbow joint, and I guess your hand is at the end over here. Right? And so this is the elbow method, and you find this sort of pattern where the distortion goes down rapidly from 1 to 2 and 2 to 3, and then you reach an elbow at 3, and then the distortion goes down very slowly after that. Then it looks like, maybe using 3 clusters is the right number of clusters, because that's the elbow of this curve, right? It goes down, distortion goes down rapidly until k equals 3, then it goes down very slowly after that, so let's pick k equals 3. If you apply the elbow method and if you get a plot that actually looks like this, then that's pretty good, and this would be a reasonable way of choosing the number of clusters. It turns out the elbow method isn't used that often, and one reason is that if you actually use this on a clustering problem, it turns out that fairly often, you end up with a curve that looks much more ambiguous, of maybe something like this. And if you look at this, I don't know, maybe there's no clear elbow, right? It looks like distortion continuously goes down. Maybe 3 is a good number, maybe 4 is a good number, maybe 5 is also not bad. And so if you actually do this in practice, if your plot looks like the one on the left, then that's great, gives you a clear answer. But just as often, you end up with a plot that looks like the one on the right and is not clear what where the location of the elbow is. It makes it harder to choose a number of clusters using this method. So maybe the quick summary of the elbow method is that it's worth a shot, but I wouldn't necessarily, have a very high expectation of it working for any particular problem. Finally, here's one other way of thinking about how you choose the value of k. Very often, people are running k-means in order to get clusters for some later purpose or for some sort of downstream purpose. Maybe you want to use k-means in order to do market segmentation, like in the t-shirt sizing example that we talked about. Maybe you want k-means to organize a computer cluster better. Maybe you're learning clusters for some different purpose. And so if that later downstream purpose, such as market segmentation, if that gives you an evaluation metric, then often a better way to determine the number of clusters is to see how well different numbers of clusters serve that later downstream purpose. Let me step through a specific example. Let's say we go through the t-shirt sizing example again, and I'm trying to decide, do I want 3 t-shirt sizes? So if I choose k equals 3, then I might have small, medium, and large t-shirts. Or maybe I want to choose k equals 5, and then I might have extra small, medium, large, and extra large t-shirt sizes. So you can have like 3 t-shirt sizes or 5 t-shirt sizes. We could also have 4 t-shirt sizes, but I'm just showing 3 and 5, just to simplify this slide for now. So if I run k-means with k equals 3, maybe I end up with that's my small, and that's my medium, and that's my large. Whereas if I run k-means with 5 clusters, maybe I end up with, those are my extra small t-shirts, these are my small, these are my medium, these are my large, and these are my extra large. And the nice thing about this example is that this then maybe gives us another way to choose whether we want 3 or 4 or 5 clusters. And in particular, what you can do is, think about this from the perspective of the t-shirt business and ask, well, if I have 5 segments, then how well will my t-shirts fit my customers? And so how many t-shirts can I sell? How happy will my customers be? What really makes sense from the perspective of the t-shirt business in terms of whether I want to have more t-shirt sizes so that my t-shirts fit my customers better, or do I want to have fewer t-shirt sizes so that I make fewer sizes of t-shirts and I can sell them to the customers more cheaply. And so it's the t-shirt selling business that might give you a way to decide between 3 clusters versus 5 clusters. So that gives you an example of how a later downstream purpose, like the problem of deciding what t-shirts to manufacture, how that can give you an evaluation metric for choosing the number of clusters. For those of you that are doing the programming exercises, if you look at this week's programming exercise associated with k-means, there's an example there of using k-means for image compression. And so if you were trying to choose how many clusters to use for that problem, you could also, again, use the evaluation metric of image compression to choose the number of clusters k. So how good do you want the image to look versus how much do you want to compress the file size of the image. And if you do the programming exercise, what I just said will make more sense at that time. So just to summarize, for the most part, the number of clusters k is still chosen by hand by human input or human insight. One way to try to do so is to use the elbow method, but I wouldn't always expect that to work well. But I think the better way to think about how to choose the number of clusters is to ask, for what purpose are you running k-means, and then to think what is the number of clusters k that serves that whatever later purpose that you're actually running k-means.